Hello friends, welcome to the course Essentials of Data Science with R Software 1, in which we are trying to understand the basic concepts of probability theory and statistical inference. So you can recall that in the last two lectures we had considered the test of hypothesis for the mean parameter or the mu from a normal population when sigma square is known and when sigma square is not known. And we have discussed that how are we going to use them, how are we going to interpret the result from the software and so on. And in software also we had considered that the software command was very general, and I had told you that that command we are going to use at that time only for one sample, and say there are some more components which are needed for a two sample test. So, in this lecture we are going to talk about the two sample test for the mean when the variance is known and variance is unknown. So, now in this lecture it is very important that the last two lectures for the cases h naught mu equal to mu naught when sigma square is known and unknown, you must revise them, because I am simply going to use the same command, same everything. The only thing what I want to tell you here that under what type of condition these tests can be used and what is the test statistic. Right. So, in this lecture we are now going to talk about two samples. You know, whenever in real life we are trying to do the data analysis, there are many questions in which we want to compare. For example, on a shopping website we would like to compare the shopping behavior of say male versus female, right? Or we can say that that whether youngsters are doing more shopping or elder people are doing more shopping. Or we can also say that that during a festival time the sales related to the clothings and the sales related to the gift items, they are going to be the same or they are going to be different. Or I have different types of questions that okay, I believe that during the festival time the sale for the clothing is going to be higher. So, I suggest my shopping website, okay, you try to give some coupons or some incentive for the customers, or you give better discount, because it is possible that not one but couple of shopping websites are going to float the sale. So, I am working for my website, so I would be interested in that thing. So, suppose if there are three websites and they are trying to give the mega sale, bumper sale, etc., during the same period. Now, the customer will have an option whether the customer wants to buy a dress, whether that dress has to be purchased from shopping site 1, 2 or 3. So, obviously, the one shopping site which is giving a better price, better discount for the same item, the customer will prefer from there. So, how to make comparisons of such thing? So, that is the topic which I am going to discuss in this lecture. So, let us begin our lecture and first try to understand the basics. Okay, so, now the first case I will take that we have a situation where sigma square is known, and after that I will come to the assumption that when sigma square is unknown. So, you can recall that in the one sample case you have used the set test, that was x bar minus mu upon sigma by root n, and then you have conducted the test of hypothesis. So, same thing I am going to use here towards the end. Okay. So, now we are more interested in conducting a test of hypothesis about the difference of the means or comparing the means. For example, in a survey of buying habits, 400 women shoppers are chosen at random in a supermarket A, and their average weekly food expenditure is suppose rupees 250 with a standard deviation of rupees 40. And then there is another supermarket where means another set of 400 women shoppers are chosen at random, and their average weekly food expenditure is coming out to rupees 220, and the standard deviation here is 55. So, how you can conclude that what is really happening in this phenomena? Do these two populations have a similar shopping habits? Means both these shopping stores A and B, they have got the similar shopping behavior for the women shoppers or for the female shoppers, or are the average weekly food expenditure of the two populations are equal, because they are trying to spend here 250 rupees and 220 rupees, but their variances are also different. You can see here 40 and 55 squares. Right. So now that is the question. So now we have a setup here where we have suppose two samples, and they are actually independent sample. Independent means both the samples have been drawn independently from two different population. Right. So the first sample is drawn from a population with say a mean mu1 and a variance sigma 1 square, and the second sample is drawn from a population with mean mu2 and variance sigma 2 square. Right. So what we try to do here, that from the first sample we are drawing a sample of size n1, and from the second sample we are trying to draw a sample of size n2. So based on this n1 and n2 observations, we try to compute their sample mean in the respective sample. So the sample mean in the first sample is indicated by x1 bar, and in the second sample the sample mean is indicated by x2 bar, right. And we wish to examine if the two population mean mu1 and mu2 are the same or they are different, right. So now I can translate this requirement in terms of the null hypothesis and alternative hypothesis. So there can be three possible alternative hypothesis against the null hypothesis H naught mu1 equal to mu2. So this alternative can be, you know, that two sided or one sided, that mu1 is not equal to mu2, mu1 is greater than mu2, or mu1 is less than mu2. Now these things are very simple for you to understand. And since these population means mu1 and mu2 are unknown, so we use the statistics x1 bar minus x2 bar to make conclusion about mu1 minus mu2. You can see here that if you assume the normal population, then expected value of x1 bar minus x2 bar is going to be, say here, expected value of x1 bar minus expected value of x bar 2. This is going to be here mu1 minus here mu2 under normality, normal distribution. So you can see here that x1 bar minus x2 bar can be used as an estimator, or rather an unbiased estimator of mu1 minus mu2. Right. So we assume here that sigma 1 and sigma 2 both are known to us, both the populations are normal, or if not normal, means we can also assume that the sample sizes are quite large, the n1 and n2s are quite large. So one point which you have to observe here, that here I am trying to write down here H naught as mu1 is equal to mu2. So this can also be written as H naught mu1 minus mu2 is equal to 0, or if you want to make it here more general, then this can also be written as mu1 minus mu2 is equal to some value here d, right. So this hypothesis can also be used if the difference between the two population mean is 0 or even any other value. Right. So this is also helpful in many applications, that sometimes you want to see whether the difference between the male and female shoppers in a shopping website has a difference of at least 1000 rupees or not, or you want to see that you have some hypothesis that you believe that females are spending say 5000 rupees more on shopping than a male shopper and so on. So these types of things can be done over here, but now we try to construct here the test of hypothesis for this thing, right. So now we know that we have drawn a sample from normal population. So I can write down here that the distribution of the sample mean 1, it is going to be here normal with mean mu1 and variance sigma 1 square upon n1, and sample mean 2 has got a normal population with mean mu2 and variance sigma 2 square upon n2. Right. Now based on that we can create the statistics. So we know that both this x1 bar and x2 bar, they are independently drawn. Both the samples are independently drawn. So what will happen here, that if you try to see that the observations of first sample and observations of second sample, they are going to be mutually independent of each other. So now in case if I want to estimate here mu1 minus mu2, then possibly I can consider x1 bar minus x2 bar as a possible estimator, and if you try to take its expectation, you can see here that x1 bar minus x2 bar is an unbiased estimator of mu1 minus mu2, and if you try to find out the variance of this x1 bar minus x2 bar, so this is going to be variance of x1 bar plus variance of x bar 2 and minus here twice of covariance between x bar 1 and x bar 2, but this covariance term is going to be 0 because the observations in the first and second sample, they are mutually independent of each other. So, now this variance of x 1 bar minus x 2 bar comes out to be here like this, and you can now write down the statistics that it is just based on say x bar minus mu divided by sigma by root n. So, you can see here I am writing here that under H naught, that means when H naught is true, that means when mu 1 minus mu 2 is equal to 0, then I can write down here this statistics x 1 bar minus x bar 2, and this 0 is coming because mu 1 minus mu 2 is equal to 0, right. So, means if you want to test a hypothesis that H naught, like here H naught mu 1 minus mu 2 is equal to d, then this 0 is going to be replaced by here d, right. Okay, so this is just for your information, but here we are considering d to be 0. So, this will become here x 1 bar minus x bar 2 minus 0 divided by the standard deviation, which is the positive square root of the variance which you have obtained here, right. So, now this is the statistics under H naught, that means when H naught is true. So, and we know from our statistical theory that this quantity is going to follow a normal distribution with mean 0 and variance 1, right. So, we use the normal 0 1 distribution to get the critical values and p values. So, now if you want to use this test in the R software, that is pretty simple and straightforward. You already have done this test, you have done the Gauss test in the package compositions when we did the test of hypothesis for mean when sigma square is known, right. So, in the same command, in the same setup, you simply have to now give here the values for the second sample. Earlier we had taken all such values which were related to the second sample as null, right. So, we are going to use here the command here Gauss DOS test. For that you need to install the package composition and you need to upload it, and after that the command here is Gauss dot test. G is going to be here in capital letter GAUSS.test, and now you have to give here the data vector. So, x is going to be the data from first sample and y is going to be the data from the second sample, and then this mean, actually mean is the value of mu 1 minus mu 2. So, if this is equal to, you have to be careful, if it is d is equal to mu 1 minus mu 2, then in that case you can give this mean to be equal to here d, some say some numerical value. But in this case, because we are considering the value of mu 1 minus mu 2 to be 0, so we are giving it to be here 0, right. Now, standard deviation you have to just specify, then alternative you have to specify whether you want two sided, less or greater, and then you can specify here the confidence level also, right. So, anyway, we try to use this test on a given set of data and we try to see what we can do here. So, now we consider here an example where we try to implement this thing in the R software, right. So, suppose there are some fishes and they are given two different types of food, two different types of diets, say A and B, and how much weight they have gained, this is reported. So, from the two samples, the gain in the weights of the fish is reported here is like this, for A like this, for B like this, and these weights are given in the grams. And suppose the standard deviation is known to be here 2, and suppose we want to test if the two diets differ significantly as regard their effect on increase in the weight, right. So, we want to test here a hypothesis like H naught mu 1 equal to mu 2 versus H 1 mu 1 is not equal to mu 2, right. So, for that I simply have to give here the data here like this. I am denoting here say data on x A as A, data on the food B as say x B, which is here like this. And now I have to just use the R command, that Gauss dot test, and then this is the data on the food A, x B is the data on the food B. Mean is equal to 0 because we are considering mu 1 minus mu 2 to be 0 under H naught, and SD is the standard deviation that is given to be here 2. The alternative we are considering here two sided, right. So, now you can see here this is here the outcome, right. It is just exactly on the same lines as we did it in the case of when sigma square is known in case of mu. So, data here is given here to be here like this, t will come out to be here minus 2, mean here is 0, SD here is 2, and p value here is 0.009823, and alternative here is two sided. So, now you can just compare whether p value is less than alpha or not. So, in case if you try to take here alpha to be here 0.95, then what will happen? This p value is smaller than case alpha, and we will say here reject H naught. That means mu 1 minus mu 2 is not equal to 0, right. Now, whether it is increasing the weight or decreasing the weight, that we do not know. For that you have to conduct the other two types of hypothesis, and this is the screenshot of the same outcome, right. And I will try to show you on the R console, but let us first consider the second test, where we are going to simply assume the same setup, but we assume that the variances are unknown to us. So, now we have done this case, that when sigma square is unknown in the one sample test for the mean, then we have to use the t statistics. So, similar type of thing we are going to use here also, right. So, when sigma 1 and sigma 2 both are known, we use the normal 0 1 distribution. When sigma 1 and sigma 2 both are unknown, then we use the t distribution, and assumptions are both the populations are normal, and we are assuming here that sigma 1 square and sigma 2 square are unknown, but equal, right. And there is a reason for that, that whenever we are trying to find the test using our statistical theory, in that test we need to find the distribution of certain statistics, and for which we need to make an assumption that sigma 1 square is equal to sigma 2 square, and under that condition the test statistics what is being reported here, that is obtained. Now, the question comes here that in case if this is not valid, then definitely we have another type of test, and that is actually called as Fisher-Behrens problem. In that problem, they have tried to address that if sigma 1 and sigma 2 squares are unequal as well as unknown, then in that case one can conduct the test of hypothesis there, but definitely there is going to be some loss in the efficiency, right. So, well, I will not discuss here the Fisher-Behrens problem or how to construct the test when sigma 1 square and sigma 2 square are unknown as well as unequal, but definitely through the software this is not a big deal. You simply have to choose the correct option, and then based on that you can conduct the test of hypothesis, but you must know from the basic fundamental what are you going to do, and that is important because many times people are trying to use the software and they try to give this option without understanding, and but software does not understand that those options have been given without understanding. So, if they do not understand these options, possibly the statistical conclusions are going to be wrong. So, now we come to our test of hypothesis. Suppose we want to test the null hypothesis H naught mu 1 equal to mu 2, and there are three possibilities for the alternative: mu 1 is not equal to mu 2, mu 1 is greater than mu 2, and mu 1 is less than mu 2. So, now what we try to do? We try to observe the two samples independently from two normal populations. So, the first sample is x1, x2, xm of size m, right, and this is drawn from the normal population with mean mu 1 and variance sigma 1 square, and the second sample is here y1, y2, yn of size small n, which is drawn from the normal mu 2 mean and variance sigma 2 square, and both are drawn independently. So, that is obvious. So, this population mean mu 1 and mu 2 both are unknown, and we want to use the statistics x bar minus y bar to make some conclusion about mu 1 minus mu 2, because you know that expected value of x bar minus y bar is equal to mu 1 minus mu 2. That means x bar minus y bar is going to work as an unbiased estimator for mu 1 and mu 2, and we assume that here obviously sigma 1 and sigma 2 both are unknown, but they are equal. That is what you have to keep in mind. So, now from the result that we did in the lecture of distribution of sample means, we know that sample mean x bar is going to follow a normal distribution with mean mu 1 and variance sigma 1 square upon n, and sample mean of y1, y2, yn, that is y bar. This is going to follow a normal distribution with mean mu 2 and variance sigma 2 square upon n, and based on that we can create the test statistics as follows, right. We know that expected value of x bar minus y bar is going to be mu 1 minus mu 2, that I already have shown you. But now for estimating the variance, what we try to use here, we try to use here the pooled estimate of variance. So, what are we going to do here? This is like this one, that you try to compute the summation I goes from 1 to m xi minus x bar whole square plus j goes from 1 to n yi minus y bar whole square divided by m plus n minus 2. So, this is actually something like m minus 1 say sx square plus n minus 1 times sy square divided by m plus n minus 2, and then this m plus n minus 2 is obtained like as here m minus 1 plus n minus 1, right. So, and this sx square and sy square, they are the quantity like 1 upon m minus 1 summation I xi minus x bar whole square, and sy square is 1 over n minus 1 summation say here I yi minus y bar whole square, right. So, now using this pooled estimator of variance, we can define here the statistics TC. So, that is going to be simply x bar minus y bar, and this 0 is coming because of this here h naught mu 1 minus mu 2 is equal to 0, right. If you want to do it something else, as we discussed earlier, you can also take it as a D, and then you can conduct the relevant test of hypothesis. And then in the denominator, this is capital S, which is the positive square root of this s square and square root of 1 upon n1, and this is square root of 1 upon m plus 1 upon n. So, this can be written here as like this x bar minus y bar upon s into square root of 1 upon m plus 1 upon n, and this is the value of the TC when h naught is 2, because when h naught is 2 only when mu 1 minus mu 2 is taking the value 0, otherwise this will take some other value say D, right. So, under this assumption we can find out the distribution of this statistics at T distribution with m plus n minus 2 degrees of freedom. And in case if you are trying to use a larger sample also, which will usually be a case in the data science, then we are going to obtain the critical values from the normal 0 1 distribution, because usually you have a condition only where the sample size is greater than 30, right, or the degrees of freedom should be greater than 30. So, that is really going to happen in data science. Otherwise, in cases if it is not the case, then you please try to choose the values of T from T tables, the probabilities of T tables. That is what you have to do, and this is what I wanted to write here. Now, I try to take here the same example, and I try to show you how you can do it in the R console. So, we have the two samples in which we have obtained the data on the weights of the fish based on two diets A and B, and so this data is given here for the diet A, and the diet B is here like this, and these values are the gain in the weights of the fishes. So, they are given in grams. Earlier we assumed that standard deviation was known to be 2, but now we are assuming that that standard deviation is not known to us, right. So, now we have to estimate it, and then we have to compute the T statistic, but we do not have to do anything. Well, if you want, you can do it manually also, but then we are going to use the R software to do the same job. Now, I have given you a sufficient idea that how these values are calculated and how these decisions are made based on left tail test, right tail test, or two sided test, right. So, we want to test here the hypothesis, same hypothesis h naught mu 1 equal to mu 2 versus h 1 mu 1 is not equal to mu 2. But now, you can see here I have to give here this data like this. I have to simply give here the same data x a and x b as earlier, and I have to use the same command, but now you have to observe where is going to be the change. The command is the same. So, we are going to use here T test, the data on say diet A, data on diet B, that is x a and x b. Alternative here is the same two sided, mu is equal to here 0, which is the value of here mu 1 minus mu 2 equal to 0 under h naught, and paired is equal to false, because we have not used the paired observation, but the difference comes over here, that variance dot equal to is now true, right. So, this is going to indicate this option, that here in this case the variances are unknown and variances are unequal, right. And then confidence level, you have to give the value of 1 minus alpha as earlier, and the output is going to be the same, exactly you have to interpret in the same way. This is here the p value, and this is here the 95% confidence interval, and since this is a two sided hypothesis, so you can see here that these intervals are given here as lower limit and upper limit. Now, I will ask you that please try to look into the earlier values and try to see that whether this confidence interval is going to be changed or not when this standard deviations are known or say unknown, right. Now you can see here this is the screenshot, and then I will try to show you this outcome towards the end, because now I understand that you are pretty comfortable with the R software, and you can see I simply have to just copy the same command there in the R console to assure you yes, that these things are working. Okay, so now this was about the t-test when the variances are unknown, but we have imposed a condition that variances are equal. Now, in case if you have a condition that the variances are not equal, my suggestion is simply that you try to use this option in the command, and then simply try to give here variance dot equal is equal to say here false, and that will use the concept from the Fisher-Barron theorem, and it will try to give you the outcome, right. There is no issue. But anyway, I am not going to talk here about the Fisher-Barron problem and the related details. Now, I try to take here one more example of the t-test where the variances are unknown. We have samples from two different population, that is two sample test where the variances are unknown, but in this case the observations are paired. If you remember, we had talked about one sample test, two sample test, and in the two sample test we had taken an example where the observations are obtained on the same unit. That means, for example, if a student has been given a test and his marks are compared when the student has been given a special tuition or training, and then the examination is conducted again. Or the same thing is this, that if I want to test the efficiency or efficacy of a medicine, then some patients are called, their body parameters are recorded, and then they are given the medicine for some time, and then the body parameters are recorded again on the same set of patients. So, these are the situations where we can employ the paired t-test. So, paired t-test is going to be applied when we have two samples, the variances are unknown, but the observations are paired. That means, on the same unit you are going to obtain two sets of observation. So, the two samples are not independent, right. So, let me try to take here a very simple example, and then I try to give you the details. Suppose there is a company in which there are some people who are working in the customer service. So, and they have to attend some telephone calls, suppose, or say this complaints, and then they have to attend them. So, now what they do, they try to provide a special training to those people, and then they want to compare whether the number of complaints after the training or before the training, is there any change, whether they have become more or less, and so on, these types of conclusion. So, this company has a, suppose here say here these salesperson, there some name is given CB, TF and so on, whatever it is, whatever you want. Now, the main thing for us is that the number of complaints which these people were able to solve before the training, this was like 6, 23, etc. And after the training, the same person attended only 4 calls, the second person attended only 6 calls, third person attended only 2 calls, and so on, right. So, now they want to test whether the training was effective or not. So, that means once again we are interested in the same type of test of hypothesis, that H naught mu 1 is equal to mu 2 and versus H 1, that can be two sided or one sided, like greater than or less than, that is mu 1 is not equal to mu 2, or mu 1 is greater than mu 2, or mu 1 is less than mu 2. So, now if you try to see in this paired sample cases situation, because we are trying to obtain the observations on the same set of people. So, obviously, the number of observations in both the sample, they are always going to be the same. So, we observe here two samples on say x1, x2, xn and y1, y2, yn from the normal populations, and both the samples in this case they are dependent sample, it is unlike the earlier case. Now, so what we have to observe here, the two samples are not independent and the sample observation are paired together. This means the pair of the observation xi and yi, they correspond to the same ith individual, right. So, obviously, in this case the sizes of both the samples should be the same, and the population mean mu 1 and mu 2 are unknown, and we use the statistics x bar minus y bar once again to conclude about mu 1 minus mu 2, as this is going to be an unbiased estimator. So, in this case now you have to observe what are we going to do. In the first step, we obtain the difference between their individual observations. and we denote them here as a di xi minus yi, right. Please don't get confused with the same d that we used earlier when I discussed that h naught mu 1 minus mu 2 is equal to d. This is something else, this is different, and we assume that here both the populations are going to be normal, right. So now we are not going to use xi and yi, but we are going to use this di to develop the test statistics. So that is why we need the mean and variance of this di, and in practice this variance is unknown to us, and even if suppose sigma 1 square and sigma 2 square are known to us, but then finding out the variance of this new random variable xi minus yi might be complicated, might be different, because the samples are not independent. Earlier finding out variance of x1 minus y1 was easier because both the samples were independent, but in this case they are dependent, right. So we try to translate this two sample case in the framework of a one sample case. How? As follows, right. We try to consider this case as a test of single mean of di's with hypothetical mean as 0 and population variance as unknown, right. So now what you try to see here, earlier you had taken the statistic like x bar minus mu upon s by root n. So what we try to do here, that instead of using here the sample observation x1, x2, xn, now we try to use the observation d1, d2, dn, and we try to find out here d bar minus here mu, which is going to be say here h naught mu is equal to 0 under h naught divided by the standard error of d1, d2, dn, means standard error of d bar based on d1, d2, dn divided by the sample size. This is what exactly are we doing. So this case is now similar to your one sample t test what you did when sigma square is unknown to us. So we are simply trying to write down this statistics here Tc, this is equal to d bar divided by Sd by root n when h naught is true, and where this here d bar is going to be as simply the sample mean of d1, d2, dn, and Sd square is going to be the sample variance of d1, d2, dn, and under our assumption this statistics Tc is going to follow a t distribution with n minus 1 degrees of freedom, because now this is comparable with the one sample t test, right. And in case if you want to use the R software to do such a test, then it is very simple. The same command continues there. The only option you have to change here, that you have to change the option of paired. Earlier you used paired is equal to false, now you have to use here paired is equal to true, right. So in this case you can see the command remain the same, t dot test, everything remain the same, only the option this paired equal to true is going to be changed, right. So now you can see here that here in this case paired is equal to here true. So now you can use them on a real data set, but I try to take here the same example and I try to show you these are the same option that I shown you earlier. So now you can see here in the same example I try to compute their di's. So you have to simply understand how are you going to write down the di's. So di is simply here 6 minus 4, or you can also take 4 minus 6, whatever you want, because this is the difference. So these are the values which are obtained by say this means 2 minus 1 I have considered here. So this will be 6 minus 20 minus 14, and these are the value of d1, d2, d3, d4 and d5. So now you simply try to find out their mean and variance, and you try to compute here this statistics, and exactly in the same way as you took the decision in the earlier case, you can also do the same thing over here. Means if you try to take alpha is equal to 0.01, the degrees of freedom are going to be n minus 1, that is 5 minus 1 4, and the critical value that can be obtained from the t table here as like this. Now you understand all these things. So in this case the value of calculated value of the statistics is coming out to minus 1.66, tabulated value is 4.604. So you can see here this is lying somewhere here. So the conclusion is accept H naught or do not reject H naught. So that means there is no evidence of a significant change in the number of complaints after the training. So the training was not effective. So now I try to do the same exercise in the R software also. So I have entered this data as YA and YB here like this. and actually this data, and you can see here is given like this y and here yb, and the alternative here is two sided. Mu is equal to here is 0, which is the value of that h naught mu 1 minus mu 2 is equal to 0. And now the only option here is the paired is equal to here true, that is t, and all other options remain the same as earlier. So now you can see here that this is the outcome, and it is not difficult to understand this outcome. It is telling you that this is a paired t test. The data is on y and yb. T star 6, that is d bar divided by sd upon root n, that is obtained as 1.655, degrees of freedom are here 4, p value here is 0.1733, and the alternative hypothesis is that the difference in the means is not equal to 0, that is two sided, and the 95% confidence interval here is like this one. So even by looking in the lower and upper bounds of the confidence interval, you can also conclude about the test of hypothesis, and this is the mean of the differences, that is d bar. So you can see here that here this p value is 0.1733. So in this case p value is greater than, say suppose alpha is equal to 0.05. So in this case you can see here means accept the hypothesis, right. And this is here the screenshot of the same operation. Now let me try to show you these things on the R console, and let me try to go back in the reverse direction so that you have no problem in understanding these things. So you can see here I am trying to take here this data on the paired t-test, and I am trying to copy it in the R console. So you can see here. So first let me try to load the library composition. Well, this package is already there in my computer, so I am only uploading it, otherwise you will have to install it. And if I try to give this data here xa, xb and this Gauss dot test, you can see here this is here the outcome. You can see here one thing you have to be careful, that here it is trying to show this value as t, actually this is the value of here z, right. So don't get confused over these things. So now we come to an end to this lecture, and now you can see that you have conducted all sorts of one sample and two sample tests for the mean. And now I think there should not be any problem. It is very easy to remember. Many times people get confused how to remember them. If you have one sample, two sample, these are the two possibilities at this moment. Yeah, they can be more than two samples also. And so in case if I am trying to consider one sample or two sample test for the mean, then there are two options. One, the variance is known and variance is unknown. So when variance is known, we are going to use the test based on the normal distribution, so called Z test, and when the variances are unknown, then we are going to use the t test, right. That is the only way these things are working. And definitely once you come to the paired t-test, then you have to just see that whether the sample observations in the two samples are independent or dependent, right, and based on that you have to choose the pair t. Definitely if you have more than two normal populations, like as we have considered here only two samples, but there can be more than two samples also, like as somebody has collected the sample from city 1, city 2, city 3, city 4 and so on. So then the null hypothesis will be h naught, say mu 1 equal to mu 2 equal to mu 3 equal to mu 4. So whenever there are more than two means, the test of hypothesis can also be conducted for the equality of their means, and this is called as analysis of variance, which you briefly call or popularly call as ANOVA. But I am not going to do here ANOVA, but surely once you have understood this one sample and two sample test, there should not be any problem in understanding those tests for you. So I will now request you that you try to look into your books, try to take some problems, try to take the problems from the assignment, and try to do them manually as well as on the software, so that you can understand that whatever you have understood from the fundamental point of view, the same thing is being done in the R software also. And in the next turn, I will take up the last lecture of this course on the test of hypothesis for the variances. But now you are comfortable with the test of hypothesis. Well, I am confident about it. So there should not be any problem in understanding the test of hypothesis for the variances. So you try to practice, and I will see you in the next lecture. Till then, goodbye.